Yeah, good morning, good afternoon, good evening, everybody. Welcome to Wednesday EMinar Day. And it gives me great pleasure to have Circé Malo Lalande speak to us today on time domain EM. But before I introduce Circé, a quick mention, because some of you may not be totally aware of the EMinar series. You can go onto MTNet and you'll find the EMinar page. When you go on the EMinar page, you'll see links to previous EMinars and presentations of previous EMinars, and then registration links for upcoming ones. And we will run now until the end of June. And the very last one at the end of June is going to be an open mic where we discuss anything and everything that people want to hear. Before I introduce Circé again, a quick advertisement for next week's talk. Jonas David of Indonesia, talking on magnetotelluric studies for exploration of geothermal resources, which should be really quite exciting. But today we have Circé Malo Lalande, and her title is there, TDEM applications for exploring for magmatic nickel-copper-PGE deposits, zooming in on the brownfield scale. And it's wonderful to have Circé present to us. As I said, we really don't have enough EM talks, and we really don't have enough very exploration focused oriented ones. So Circé, as you'll have seen in her CV, graduated from Laval and then a master's from École, and has been working in the mining industry since. And she's currently a senior geophysicist at Canadian Royalties, which is a nickel-copper-PGE producer. And she's been continued promoting geophysics at the college and university levels. So, Circé, I'd like to stop sharing now and hand over to you.
Thank you very much, Alan, and thank you everyone for being here today with me. So I'll share my screen. This. So trying the oh, okay, that's the
presenter view.
Yeah, it is. Is this okay now?
No. Whoa, no.
We tested it earlier and it worked. And now,
yeah, it always works when you test it.
Let's start again. Just select the right one here. Now.
That's it. That's it. Yeah.
That's good?
Yeah, perfect.
Okay, great. So I'll just change my pointer here. Okay, so you see my pointer here around scale?
Yes.
Okay, great. So my presentation will be about time domain electromagnetics application for magmatic nickel-copper-PGE deposits, and the brownfield scale is really important in the example I will present, because I work for a producer, like Alan said, and it's really rewarding to work for a company that actually operates all year long with many mines, open pits, and underground. And exploration is running all year long as well, except for we're stopping the drills when there are blizzards, obviously, and for Christmas. So we get to drill test the geophysical signature and to see the core, and that's the ultimate response. So it's really exciting, and I will share a few of, I think, great examples here that I have. So the presentation will go as follows: geological setting, physical rock properties, a little bit of theory, and then a selection of very exciting EM profiles and contour maps. So Canadian Royalties Nunavik nickel property is located in northern Quebec here. It's really remote. Access is only by plane and by boat during the summer season. And if we look at the zoom here, the property is located in the Cape Smith Greenstone Belt. And we are two actually companies exploiting nickel over there. There's Glencore and Canadian Royalties. So geology-wise, the volcano-sedimentary basin into which we are exploring is located over the Superior Province. And we have a sequence of three distinct units, or formation, should I say. The Duma Formation at the bottom. And then over we have the Beauparlant Formation, which is composed of volcanics, mostly basalts, and sediments. And on top of which there's another formation, the Puvugnito group, and that's mostly sediments. And what you see here to the right is the Expo intrusive suite that is coming from deep down, and it's got through the basin and went through the basin at specific location here. So we have ore bodies located at the contact of the Beauparlant in the Puvugnito group, and we have also other deposits located in the formation on top here. These are geologic map. On top is a plan view, and at the bottom, it's a 3D plunging view that shows how the system came from the mantle, getting towards the surface and flowing through the volcano-sedimentary basin. And the intrusive is actually the purple and orange layer there, and the basin is what is gray and green. And you can see from the shape of the intrusive that it has been a very turbulent setting. So the intrusion is twisted, its boudinage is splitting and curving, and so it's a very dynamic event that occurred when the Expo intrusive suite took place. And after that, the whole area has suffered from an intense deformation stage. And ultimately, our property geology is composed with lots of faults, anticline, syncline, and it's heavily disformed. To the right here, that's a schematic of the shape of a tubular shape intrusion with, at the bottom, the massive sulfide ore. So speaking about ore, this is the typical texture that you will find with magmatic Ni-Cu-PGE ore bodies. So all around you have the country rock here, and on top of the ore body you have a blebby texture, so big droplets of sulfide, under which you have the net textured mineralization. And at the very bottom, because of gravity, there's an accumulation of the massive sulfide texture. And I'm mentioning here that having this intrusive in a sedimentary country rock, it was very key to having economic ore bodies, because even though the magma comes from deep under and it's full. It's filled with, nickel, copper, sulfide. It really needs to get in reach with sulfur to be oversaturated and then precipitate economic ore lenses. And now let's have a look at core. So we have those same texture that I just mentioned. So you can see here nice blebs on the inside the ultramafic rock. We see disseminated texture here. That's our net here. And a nice way to know when we really reach the net texture is that the grains are interconnected, and you can put an ammeter on the core and you will see that current is actually flowing. And ultimately at the base of the system, you have massive sulfide. And the ore is mostly composed of pyrrhotite, pentlandite, chalcopyrite, with also cobalt, platinum, and palladium. These are our key commodities that we're exploring and producing. This piece of core is the argillites from the volcano sedimentary basin. It's what is really dark is graphite, and what is shiny is pyrrhotite-rich veins. And those veins are purely barren. They have absolutely no economic value, and they are running throughout the property on kilometers, and they represent a real challenge when it comes to interpreting electromagnetic survey results. So here we have a few examples of magmatic Ni-Cu-PGE deposit worldwide, and our one of our case here at Canadian Royalties Properties is here. So you see the blade-shaped dike and the mineralization at the bottom of the intrusion. And among these, for example, it's interesting to point out that our host rock is actually mafic, ultramafic rocks, and we have a lot of peridotite. And peridotite is a magnetic lithology, and so it's very convenient to track it from magnetic surveys. So these are example, but let's look at our lenses at Nunavik Nickel project. So that's a few of the many deposits and mines that we have over the property. And you know, before you raise the question, the geological setting for magmatic Ni-Cu-PGE exploration and production is that you will find many small lenses. That's how it works. The system will deposit many lenses here and there, and ultimately there are chances that you find a big one, you know, with 10-20 million tons, but in the end it's more often the case that you will find smaller lenses, and that you will have to mine multiple ore body at the same time. So here what we're looking at is to the left long views and to the right section views. And so we have 1, 2, 3, 4, 5, 6 examples here, from teeny lenses to larger bodies. That's more than a kilometer long here. And all those ore bodies are in red, but they actually represent all the texture I showed previously. So part of those envelopes are disseminated, net texture, and massive. You see also that they have a very different shape and geometry and can be buried at any vertical depth. So let's talk a little bit about physical rock properties. We drill at Nunavik Nickel, so we have access to the core all year long. So we take the advantage of measuring our core with a susceptibility meter and a conductivity meter as well. And the pentlandite and pyrrhotite are extremely conductive material, and they actually range outside of this graphic here. To the right, we see measurements that have been collected over core over the past, and we can see from the different mineralized texture the range of conductivity that we should expect. So with no surprise, massive sulfide is the most conductive feature here, reaching more than 50,000 Siemens per meter. That's incredibly conductive. Net texture is an order of magnitude less conductive, and as expected, disseminated sulfide will show no EM conductivity. I will have a word about this in the next slide. And those two lithology here at the bottom are associated to our country rock. So the sediments that are rich with pyrrhotite vein will return intense conductivity values. So that's important to take into account, because at some point they can be very alike our exploration target. And the graphite in our case is less conductive. So a small word about the disseminated sulfide texture. What we're looking at here is a geological section with three drill holes that were completed, and the color is associated to the different lithology that was intercepted by the hole. And in those three cases, we intercepted ore body sulfides, and what you see in red, the profile, that's the conductivity reading over the core. And I am zooming into this drill hole over here, where we have in orange 10, 15 meter of disseminated sulfide. And surprisingly, we see that those sulfide do yield a conductivity response. And I want to show you the core for this hole, because this is something that happens. It's because, you know, with mapping, we need to be representative of the ore envelope. So we can't just map each little veins, you know, we need to get a, you know, broad picture of the ore envelope. So often disseminated sulfide zone will actually include a few veins, and that's what we see here. So we see that there are two massive sulfide areas on top and bottom, and that's what I highlighted here in red. And in between in orange, that's our disseminated sulfide intercept. And you see here with the white arrows that I pointed some veins that were intercepted with that hole in that disseminated sulfide sector. So it's actually good news EM-wise, because it means that if we were to do a borehole EM acquisition, for instance, we could actually probably track what we call disseminated sulfide. So that's my theory slide. I like to keep things simple, and I prefer color and vectors to equations. So when we speak about time domain electromagnetics, we speak about basically three laws that are implied. We use Ampere laws. So when there's a current flowing in a wire, there's going to be an associated magnetic field that's going to be generated. Ohm's law, because when we have a circuit, we can have, we know voltage, resistance, and current will be tightly related. And Faraday laws is the key, because when we have a magnetic current, a magnetic field, going in an area, if we change that magnetic field, where there's going to be induction in the ground or anywhere else, if there's any conductive material in the vicinity. So that's the basics. And to the right here, what we have is the waveform of the time domain EM system. So basically, we flow current in a transmitting loop, and we shut the current. So that's our electromotric force that is inducing eddy current in the conductors. And then we have a time off here with no current anywhere, and we record the decay of those secondary fields that are coming from the induced conductors underground. So let's show an EM configuration with nice pictures. So what we have here is a picture collecting from an helicopter this winter. And it gives you an appreciation of, first of all, the great tundra. In winter, this is a fantastic environment, beautiful. And you can see here on the ground all the traces of the loops that have been displaced from station to station along survey lines. And we have to the left here the transmitter and the wire here. And we have here middle top the sensor that collects the secondary field during the off time. And the optimal way of doing ground EM acquisition for magmatic Ni-Cu-PGE exploration, given our geological setting, is to use very low base frequencies to be able to capture all the EM signal from the ore lens, given that there are some great regional conductors lying there also. B field measurement with 3 components is really key. We're looking at very good conductors, I mentioned that, but we're also looking at lenses that can be small, they can be vertical, flat lying, twisted. So we need to have every of those 3 components. Why is important, and I will show an example along the way. Moving loop also to make sure that at some point during the acquisition, we will have a situation with maximum coupling with the ore target. And we also need tight line spacing because some of the lenses, like I mentioned, are very restrained in shape and size. So what do we need to have a success when we're doing time domain electromagnetics? Well, there's a lot of parameters involved. There's actually quite a few. So when we look at the instrumentation and the configuration, we need good timing settings, stable and high transmitter current, a very sensitive sensor. In our case, we're using the squid from Supercon, the high temperature squid. Loop configuration has to be optimal, loop size, location. Now we need to have a very good understanding of our geological target and setting, nature, texture of exploration target. In some areas, our lenses are purely disseminated sulfide with a little bit of net texture. So we need to adapt to those possible targets, shape of the target, size, depth, and the global setting. And of course, I mentioned that we were working on the property where there are active mines. So mining infrastructures, cultural noise is definitely part of our reality. So we need to be careful also with that variable. So let's jump into the examples I wanted to present to you today. That's an easy one. So I'll start slowly. So we have here a very boring geological map of volcanics, and there's no outcrop of any mafic, ultramafic intrusive. What we can see in thick gray here are the formational I was mentioning. So that's the pyrrhotite-rich veins inside the sediments, and these represent important EM conductors. There's a discovery over there that was made in 2007 from an airborne VTEM survey, and those are the results. So what we see here on top, those long conductors, that's the shaded conductivity here. We see the long regional conductors here, those are the formationals from the sediments, and we see that little isolated anomaly here, that's a little conductor that's popping out of this area, and that's a massive sulfide deposit. And just here underneath, that is the magma, and we can see that first of all, the formational are also conductive feature, and we know in our case the pyrrhotite is magnetic, so you can see it here, those long magnetic lineaments, and we also see that little discrete mag feature that is associated to the host rock, which is peridotite. Let's have a closer look at the mag map. So we really see that the peridotite is popping out of the magnetic results, and you can see also those long trends associated to the pyrrhotite veins. I mentioned that the peridotite is very magnetic. Unfortunately, in some part of our property, the exposed fluid intrusive is most likely composed of pyroxenite and gabbro, which are not magnetic. So in this case, when we look for, a new area to explore for additional intrusion, we need to find for breaks in the formationals. And that would be the location where the non-magnetic intrusive would have cross-cut the basin. There was a bead field ground surveys that was carried out over that area, and those are the two plan maps here to the right. So on top, that's early time results. So you will see in the presentation, I'm always referring to the channel number and the time after the turn off time for reference. And so we see here a little massive sulfide deposit located among the peridotite short units. And that signature had a lot of signal even later in time. This is a later time contour map, and we're now at 150 millisecond after the turn off time, and there's still a lot of current, a lot of signal, and we see that there's still also a lot of signal with the formational unit. This slide is to show the numerical modeling resulting from this result. It's really a teeny ore body, I admit, and it's the teeniest that we have, but it's under production. It's rich. It's worthwhile to mine. One aspect I mentioned about tight line spacing is for this particular one. If we had discovered it with ground moving loop acquisition, having carried out 200-meter line spacing, we could have missed it, and that's would have been a shame. It's subcropping, easy to mine, a little open pit, so very important to keep the line spacing really tight. The numerical modeling is performed using the Maxwell software. That's a plan view here, and I'm sorry that again the ore body is really teeny. And at the bottom here, you see a looking west view, and you can appreciate the difference between the size of the ore body and the formational plates here. At Canadian Royalties, we do a lot of modeling, and so we are separating the conductors into 3 groups of distinct plates to get a feeling of where's the most conductive features. So low conductive plates will be blue, the moderate conductors will be green, and the higher conductance plates above 10,000 Siemens will be yellow, and we like to chase yellow plates. However, I will present an example that that shows not only the yellow plates should be of interest. And this is just to show the fit between the measured data in black and the calculated response from the Maxwell model in red. And you see a formation over here, and you see the very short wavelength shallow ore body here. So that was the easy one, number 1. And now I'm presenting another easy one, number 2, in terms of less challenge, let's say, to get from geophysical result to discovery. So that's another area of the property. And again, what's pink, purple, and orange, that's our intrusive. And you see it's cross-cutting the basin again, like this here. And to the right, I'm showing a residual magnetic intensity map. And you can appreciate how dynamic the intrusive is. There's a lot of, like I mentioned, kinks and boudinage and splitting. And I like to see this area here where the intrusion becomes a gabbroic lithology, and so we totally lose its magnetic signature, but it's still there. And we also see that the pyrrhotite vein actually, can be also delineated from the MAC survey. To the bottom here, that's a VTEM compilation that has been carried out a few years ago. And to the left, we have what we call the early time map, and to the right, that's the late time map. And Early time for VTEM system is not the same as early time for a low frequency ground B field acquisition, and I will give more information about this a bit later. But if we look at those beautiful color map here, what we can see is that first we really get a good feeling of where our formationals are, and they are remaining with time here on the VTEM. We also see that the intrusion is really post-dating the basin, so it's cross-cutting those markers, and it's absolutely resistive. And the VTEM did detect a ore body that we have here. It's a shallow ore body, and it's waiting to be mined. Now let's look at the B field moving loop acquisition over the area. So moving loop EM is to the right, and what you see here on top is the early time, and it's actually what I would think would be a good comparison with the late time of the VTEM. So VTEM is 30 Hertz, so I'm presenting here a channel close to 7 milliseconds after the turn of time. And what we have at the bottom, that's a later time, channel 38, 300 millisecond after the turn of time. So let's compare both plan views on top, the VTEM late time and the moving loop here at measure on the ground. Let's have a look at the formational here. So what we see from the squid results is that those formational have a much broader signature, highly with the difference in terms of loop size. Obviously, the airborne system loop is limited with what the chopper can actually carry. And here on the ground, we have larger loops. So we get the deeper portion of the body to get induced. And from the ground survey, we also get a good feeling of the dip and depth extent of those formational. The signature that is interesting here is this guy over here. So that's an isolated EM signature. It's so short, discrete. So we like those signature, and on top of things, it's located among the mafic, ultramafic intrusion. So that's a really exciting signature, and it also remains with time. We can see it here with the late time moving loop EM response. And that's a exploration success. So it has been drill tested, and we discovered a brand new ore body over there. It was quite deep, 200-meter vertical. And I want to point out that in that map over here, there's another deposit that is hidden, and it's this guy over here. That's also a deposit. So it gives you a perspective of how small the footprint of an ore deposit is with regards to the whole basin that is scribbled with formationals. Let's look at profiles now over that specific deposit. So those are distinct profiles. The lines are 100-meter apart. And what we can see is the intensity of the deposit signature that is highlighted here with the red rectangles. And you can see the amplitude is extremely low as opposed to the formationals. And what we can see also, it's a flat-lying body with a typical single peak anomaly and minus to plus signature on the X component. And I like this example because it shows how efficient the Y component is to point the center of the conductor. So you see here that the lines located at the western side of the deposit are pointing towards the center, and same for the profile located on the east end of the deposit, pointing back to the center of the conductor. Obviously, center of the conductor doesn't mean center of the ore body, right? Because like I mentioned, the nickel, copper, PGE magmatic ore bodies are composed of massive sulfides, but mostly of net and disseminated sulfide as well. So the core of the ore body may not be the conductive center. Okay, so these two examples were what I consider easy ones because there was no superposition of signature. They were isolated with their proper EM response. And the next two examples I will present will be about more complex profiles. So we have an example here where we're looking here at a result from a specific line. So we have here channels 10 to 25, so early to mid time. And what we see is a typical M-shaped anomaly suggesting the location, suggesting the detection of a dipping conductor, dipping north here like this. But when we look at the late time time gates, those are channels 38 to 43. We see something totally different. We see an M-shaped signature, but with a dip to the south and probably a more vertical feature than what was detected on the mid-time channels. And when we gather all those channels all at the same profile, we see that we really have two distinct conductive source that is generating this single profile. So we have our conductor here that is highly formational, and we have here appearing around channel, I don't know, 37 maybe. We have a distinct ore body. Well, I know it's an ore body, but let's say we have a distinct late time signature that appears, and that's exciting for exploration. So same example, but with plan view. We're looking at this particular line here. That's the survey grid that you see over here. And what we see is an anticline here in the basin. We see that we are in between two segments of the mafic, ultramafic intrusive here. And this is the magnetic map that I always like to present. So we see that our peridotite intrusive is definitely detected by the mag survey, along with in a more less intense way all the formational, and that's a dike, probably postdating everything else. So again, the formational are helpful to map the basin and to get a feeling of what's going on out there with that big deformation stage that occur after the intrusion took place. To the right here, we have again early time channels and late time channels of the ground EM acquisition. So we're looking at very early time here, roughly 1 millisecond after the turn of time, and that's very late, almost 500 milliseconds after the turn of time. And what we see is the two signature I was presenting to you as profile in the previous slide, but we see here, we really capture this EM signature of the basin here, the full anticline that is created with the pyrrhotite veins. And we see here in the late time, the massive sulfide ore body popping out in the late time. And also that's very late time, and we still have a strong response here from the basin. So again, very challenging environment when both formationals and ore bodies are stacked one over the other. I'm presenting here the model plate out of this survey grid. Very important to model every conductors, because ultimately mapping the basin is key to vector towards new discoveries. And I didn't want to mess too much around with bringing in 3D views of the model, because it's there's a lot of plates out there. So I just added some arrows to give you a feeling of the dipping of the plate. So you see here the anticline, and you see here also you get a feeling of where the dip go for the the pyrrhotite-rich but barren veins. And in red here, that's the ore envelope with 2 plates modeled out of the moving loop survey. And at the bottom, you see the fit between the calculated and the measured data. And in general, Maxwell does a great job in allowing to reproduce those type of signatures. Here, I'm just showing what we can do with calculated profile. We can grid the synthetic model response and compare plan maps of particular channel gridded. So on top, that's channel 10, that's the measured data, and that's the model data. So obviously there will be some discrepancies, but you can see if you were able to get most of the response out of your model. And what is of most interest in our case is the late time. So that's channel 40 measured and modeled. And I think that's a pretty satisfying fit over here too. So that was the stack example number 1, and now we're looking at a second example where the formational and the ore body were stacked one over the other, bringing challenge with EM signatures. So what we see here, again, geological map. Now we have a syncline over here. We see in thick gray again the formationals. And we see the mafic, ultramafic intrusion here that host showing here. That's disseminated, so it's not yielding any EM response. And that's a mine over here at the far west end of the map. And you can see also that something's going on here. There's a superposition of the folded formational, and likely the intrusive goes underneath. An appreciation of the map signature of the sector. Again, we can clearly see the formational, and just a bit of physical rock property here while I'm speaking about this type of setting. So just to show that the most magnetic feature, as expected, is the peridotite. Pyroxenite, like I mentioned in Gabbro, are favorable rocks to look for when we were chasing ore bodies. However, they have no magnetic signature in our case over our property. And we also see that the second magnetic feature here, that's the pyrrhotite-rich sediments. And again, picture of those nasty argillites. So getting back to EM now, I'm showing here the late time V10 map for this area. So again, intrusion is really resistive, cross-cutting the formational, and we see that gray conductor here. Now I will compare against the ground results. So again, early time here for the moving loop EM and late time. And what we see is that, again, the ground survey will capture pretty much what has been captured from the airborne acquisition in the early time. And what's interesting to us in the late time, some discrete conductive body will remain visible. And that's what is interesting us. We have a few distinct signature here. We have that guy over here, and we have 2 anomalies here, all late time, that are of interest, and I will be presenting individually in the next slides. These are just to show the difference, because I'm comparing channels between VTEM and ground B field moving loop acquisition, but obviously we're not comparing apples here, even though I'm showing the same time gate. Obviously 30-year system will have a on-time duration that is much shorter than what we will get at 0.25 Hertz. So let's look at the guy that was, I'm going to go back here, that guy here, that anomaly. Let's have a look at its profile. So really interesting profile here. On top, we have all the gates from 25 to 43. And at the bottom, that would be the equivalent of a 30 Hertz airborne system response. So channel, down to 8 milliseconds-ish. So there are features that are common to both profiles. So this M-shaped signature here, and we have another M-shaped signature here. The south leg is hidden in the north leg of the ladder. And what's really interesting is there's definitely a discrete signature emerging out of channel 41, 42, 33. There's something totally distinct, very conductive that is being detected at very late time. And we drill tested that exciting signature. So we're here just north of the location of the intrusive. And unfortunately, we didn't hit any ore, and we didn't hit any intrusion either. That's the physical rock property measurements over the core. So you can see there's a lot of conductive sediments out there, and we did a borehole EM acquisition, and we were hoping for a awful, late time awful anomaly, but unfortunately, we actually got a perfect meaning that, hey, your target is explained. So that's a technical success. So we knew, the source of that exciting signature was unfortunately just barren paratite veins. So now let's look at those two signatures here, late time, discrete, also very exciting. This is an example of the typical profiles that you have here. So we drill tested that anomaly, and fortunately, we did hit mineralization. Forgot to mention on the other slide, but those are the moving loop EM plates that we were chasing. There's always an adjustment with plates when we do, obviously, borehole EM acquisition. We fine-tune the model. And in this case, obviously, the veining that we hit was really conductive. And from the borehole EM survey that was performed, we confirmed that we had hit our target, and that's an exploration success. So really hard to say, with a single profile, even though there's a late time anomaly, if ore lies out there, we need a good control of the geology. It has to make sense, to find ore out there. Obviously, we're always eager to find new intrusive that are not outcropping, meaning that it's not because it has been mapped as volcanics that there's not something lying underneath, a mafic, ultramafic intrusive. So, but we really need to, stack a lot of geoscientific information to be able to optimize discovery rates. So I'm just showing here two profiles. That's the successful one in black. And there's another one here, late time signature. It's probably deformational because it doesn't look like it's a discrete signature. However, doesn't mean that there's no superposition of multiple conductor of different nature. So furthermore, with the stacked anomaly style, that's the sandwich style challenge I call. We have an area over the property where we have 2 mines on each side. We have 2 5 kilometers in between. We know there's a fertile mafic, ultramafic intrusion, but we are stuck with our area of interest here. That's a geological section, and we are actually sandwiched between paratite vein in the sediments. And you see they are really conductive in red, and that's really challenging because then we know that the surface acquisition, will be less performant because there's so many conductors out there. It just decreases the radius of investigation. This is the plan view here of the known ore body that we see on the section here, and that's the location of that specific hole that we drilled. And what you see here is the profile from the borehole EM acquisition. And what we see from this profile is 3 in-holes that are actually associated to our formationals. And I'm taking a moment here to present the total mag field profile. Surveying with a B field sensor, we can actually measure the total mag intensity profile while doing borehole EM acquisition, and it's very complementary to see the mag signature of course, our barren pyrrhotite veins, but also if we drill right next to a peridotite intrusive, then we have the opportunity to see a awful signature on that profile, and it's very handy because it will tell us that we're near a favorable lithology. Okay, so this is the model resulting from that borehole EM acquisition. So you see the 3 units for the original conductor and the fit here. And what we do in this specific case is we kind of do a reverse engineering process. So we use the modeling to actually hide plates that that would have the signature of a ore lens. And so we try to find out at which distance from the hole can we detect those hidden plates. So in this case here, that plate is too close to the hole because there's no offhole on the measured data, and we see an offhole anomaly on the calculated results. So probably that means that at a 45-meter distance from that hole, given that geological setting, we would have detected ore lens. So we're using the work reversely to actually, especially in the presence of formational located over and below our area of interest. We're trying to find out what's the radius of investigation that we were able to get with each borehole EM survey, and that will allow us to adapt our drilling pattern, more dense or less dense drilling to really track ore body in a specific area. Now let's compare a few moving loop time domain EM models with borehole EM models. That's an example here with ore body you see in pink. And that's the guy that we spoke about a bit earlier over here. And what you see here, that's the model plate from the moving loop acquisition. And when we performed the moving loop acquisition, the ore lens was already discovered. And when the modeling was done, I intentionally ignore all the borehole EM plates because I really wanted to have an objective modeling to be able to see what I could get out of the moving loop survey. And what we see to the left is the moving loop model, and to the right, that's the borehole EM model, along with the plates from the moving loop that I've kept here in black. So what we see is that the north leg of the ore zone doesn't seem to have been detected from the moving loop acquisition. And we can also see that probably the eastward continuation here has also been missed by the ground survey. Obviously, models will be different between borehole EM and surface acquisition, given multiple reasons. The station spacing is different. The sensor is not located at the same spot. Being in the rock next to a conductor will give a much greater sensitivity. And also the heterogeneous nature of the nickel copper deposits, with the probe, the downhole probe being next to the ore zone, obviously plates will more represent the heterogeneity of the mineralized envelope. So we're looking now at a long view of that specific ore body with both model plates stacked one over the other. So in black, we have the surface plate, and in color, we have all the borehole plates. And I think it's really interesting to see that both models agree with the depth to top and the downward extension of the ore zone. And there's actually an insight here. Probably there's more to find to the west, or the west portion of the ore body, you know, and that insight comes from the moving loop acquisition. Also, we can see here that probably the eastern end of the mineralization has not been well captured by the moving loop acquisition, probably due to, you know, the depth to top that we're at here. We're, you know, below 300 meters, so it becomes challenging to close to the detection limit, actually. And I'm showing here fits between measured and calculated profiles. On top, that's the borehole EM plates calculated with the ground acquisition. And you see the fit is really good. And what we have at the bottom, that's the fit with the moving loop plates. And I think both results are really acceptable. However, we know now that there's probably we actually know that there are two conductors. There's a north branch and the south branch, and probably adding the north branch to the ground model would have helped to fine-tune the adjustment here. However, when we interpret moving loop results, you know, we got to keep things simple, and we can't take for granted that, you know, a given conductor will be, you know, split into different ore bodies, or so it you know, ultimately it has to be a more simpler model. That's another example, moving loop models versus borehole EM models. That's an anomaly I presented with the second example. I call it example easy one, number 2. So what you see here, that's a green plate. It's a 3000 Siemens plate, and it explains the measured moving loop results. And at the bottom here, you have the smaller plates coming from the borehole EM survey. So on top, plan view of moving loop against borehole EM plates, and here at the bottom, looking north view. What we see is what you can expect in terms of precision with, you know, moving EM modeling. So obviously, we see now that the ore zone is actually plunging eastward. However, this has not been captured from the moving loop. And I like this example because it shows that as we were intercepting, this is the discovery hole, and as we were drilling to the east and intercepting more ore, at some point in 2017, we were there, and the borehole EM signature were all pointing, you know, west, saying here on the Y or D component that the core of the conductor was located in the west. So at some point where you're at depth, and I will show you here, you know, we're below 200 meter, 250 meter deep, and we have a thin section now. And even though the plates are 10,000 Siemens, there's a decision that has to be made. At least, you know, is it worth pursuing drilling, you know, at that depth, given the thickness, the thinness of the ore zone? And that's the perpetual challenge with EM. You know, is it thick? Is it just conductive? Is it both? In this case, however, we figured that, and a bit of geological results here. That's the core here with the veining zone here, the massive sulfite. So it's great, but it becomes to be thin at this type of depth. So we figured that we would displace the transmitting loops to the east, to actually stop energizing the same known portion of the ore envelope. So we were looking to find if there would be another conductive core to the east, an extension, something significant. So we actually moved the loops, and you see there are two loops, and I will have a word about this in the coming slides. So we displaced the loops to really focus our primary field on the eastern portion of the ground EM loop, ground EM plate. And then we drilled that hole in 2018. And we intercepted more mineralization. And also what was exciting is that now the white component of the borehole EM acquisition was telling us that, hey, there is something conductive to the east also. So this example is to show how the location of transmitting loop is key to this type of exploration. And then after 2018, we continued drilling. So that's the updated model now, what we have so far from 2021. So we drilled, and you have the location of the actual ore envelope here. So we did extend the ore zone further down east. And we did also complete and populated the ground plate now with more borehole EM plates, which makes sense because there was EM signal over there to be explained. And to the left here, you see now the comparison between the ground plate and the borehole EM plates here. And this last image is just to show the location of the borehole EM surveys, and also that there's still some plates to be tested. They are green, so meaning they're probably of less conductive material. And we have to think altogether if it's worth to pursue the drilling or if we stop here. But we feel now in 2021 that geophysics really helped to get a more clearer picture of that ore body. So a word about borehole EM loops. I'm showing again, a few of our deposits here, and I will focus on these two here. So we have that guy, vertical ore body, and we have this one here that is dipping to the north at 45 degrees. So obviously, we cannot do moving loop EM when carrying out borehole EM acquisition. So we need to decide where we put the loop. And so if we know that the ore length is vertical, then we'll put the loop at the right spot to ensure maximum coupling with the conductor. However, knowing the shape of the conductor is a luxury we don't always have. So we may end up in a situation where we are actually in a minimum coupling situation. So to avoid having such a situation at Nunavik Nickel, we always carry out borehole EM acquisition using two loops. So those are sequential acquisition, and we end up with two distinct profiles. And to the left here, that's an example of how we need to adjust our loops with mining infrastructure. So we had to lay out a loop around the pit here to produce the loop optimal for flat-lying potential ore body. And we also put the loop to the south here for allowing the detection of steeply dipping ore bodies. We are doing brownfield exploration, like I mentioned, and so often we are looking around known deposits because we all know that the best place to find new mine is next to a known mine. So we apply that logic most of the time, and this is an example here of a known ore body that you see here. And the idea with that drill hole was to see if there was anything, any satellite ore body behind and underneath that massive sulfide lens. And so we intentionally located the transmitting loop to make sure that we would actually, null couple the known mineralization, and at the same time try to make sure that we would detect flat lying or vertical lying new ore zones. And in both cases, you see that the fields are actually, you know, closely null coupling the known ore body. And these are the resulting borehole profiles. And what you see, the North Loop was successful in not detecting the ore zone. Unfortunately, nothing more was detected. And with the South Loop, there was a subtle anomaly here on the mid-time channels. Was it the ore zone detected? Yes, it was. So that's the late time signature here. And you see the superposition of the measured data in black and the calculated data in red. And what we have here is the model plate resulting from those oral EM results. And you can see a discrepancy between the ore envelope and the conductive plate. And that happens often. It's because the ore envelope, like I mentioned, includes the disseminated texture and all what's economic for mining, and it's not necessarily you know, associated to the orientation of the connection between the sulfides. So again, unfortunately, in this case, only the known ore zone has been detected. A word about borehole again, loops. So that is a thicker ore body. I've shown plate-like ore bodies, but that's an ore zone that is composed of two, we call them pods, or, you know, potato-shaped and ore envelopes. And we see the effect of using two distinct loops. So on the middle here, we have profiles coming from the South Loop. And what we see is a clear awful response with the X pointing above. And that's representing the induction of the elongated portion of that ore zone. And it looks like it's crossing, but it's actually really awful. We did not intersect that ore body. If we look at the right, the profile to the right, then what we see is actually something totally different. It's actually a crossover on the A component. I know it's a little bit subtle, but it's minus to plus crossover on Z, and on X you have a positive peak. And that means that we are following a conductor that is running subparallel to the drill hole axis. And this means that we probably energize with that loop over here, the continuity of the ore body, but the width of the ore envelope here. And two things about this example is that, you know, obviously having two different distinct profiles for each drill hole will better constrain, you know, the modeling and the ultimate interpretation, but also it may end up with reverse coupling signatures, but, you know, it's not something that we cannot handle. Maxwell does a great job with recovering the final geometry, even though the conductor is energized upside down. A word about end of hole buildups. We all like to see a late time buildup at the bottom of our drill holes. This is a ore envelope that was in the definition drilling stage. And we realized after doing borehole EM acquisition in both these two holes that there was a little beginning of a awful signature that could be detected. And we like to see these things, especially with two adjacent holes. It means that there's probably something hiding, you know, at depth. And so we modeled that signature and we drill tested it, and it was a success. We actually discovered a new zone, you know, south of that known ore body. And this is a great example. You know, when you're at the definition stage, drilling of an ore zone, you know, it's always nice to select 1, 2, 3 drill holes that you will actually push a bit downward, and then you can scan the neighbor using you know, borehole EM, and you know, there are chances that you will find, you know, satellite ore bodies, and that's what happened here. So that's my last signature. I don't know what I'm doing with time. Exceeded the time a little bit, I'm sorry. So that's an example I really like, and I'm finishing with this one. So we have our ore zone here on plan view. We have this drill hole here, drilled to the north, and we were trying to scan what was, you know, at depth to the north. And when we did the borehole EM acquisition with both loop, we got a, you know, broad awful signature with the north loop. These two profiles are with the same loops. That's the signature from the ore zone here. And then we had to model an additional signature to fit the awful signature here. And the resulting plate is a large plate, like 400 meter by 400 meter, and you know, less than 2,000 Siemens, and it looks like nothing. It's broad, and we knew there was some veining around here, so you know, not a sexy plate to follow up on. And that's the section view here. You can see where the plate is localized. However, there was actually an ore body hidden in that plate. You know, ultimately, the hole is, you know, 100 meter, 150, 125 meter away from the edge of the ore zone. And you can see that ultimately that plate was actually just, you know, an average of all what was lying out there. And there was some veining around there, but there was also an ore deposit. And you can see here to the right, the comparison between the original plate and what we have actually drilled and modeled from the borehole EM, and the little deposit that we actually found there. And I like this example because when we're doing brownfield exploration, we can always do the exercise of, you know, selecting a drill hole that is a bit far away from a known zone and see what type of plate it's going to yield, you know, as an awful. And ultimately, we don't want to drill test every of those low conductance plates, but it's just, you know, if it's well localized near a known deposit, maybe it's going to have more interest than others. So don't underestimate low conductance plates. So in conclusion, there's a lot of factors, variable involved with having success, you know, exploring for Ni-Cu-PGE magmatic deposits. And I just hope all those examples were rewarding to you. I have not shown anything new or new development. It's just using whatever's available in a smart way, I think. So I wish to thank my company, Canadian Royalties, my management, and my precious exploration team. We have a fantastic team at CRI. I wish to thank Internet EMiNARs for educating us since the beginning of the pandemic, and I hope it's gonna continue. And also I wish to acknowledge my exploration partners. So I'm happy to answer any question if there's still people in the room.
Oh, absolutely brilliant. So it's rare that we we get insight into such developed ore bodies, you know, that we go right down and we can see how geophysics is fabulous. You know, as the academic world, often we don't get that deep into the real world, so to speak. Well, you've got a load of questions rolled in, which is great. And I've got some if we run out, so I won't stop this if questions are come, and we still have 50 people online, which is, you know, this is one of our biggest ones. We had 65 at peak, so well done.
Thank you.
Yeah, you kept the audience. So I'll hold my questions to the end. I think the first one we'll ask. I'll read the questions out so they get in the record. in
Thank
the
you.
video record. First one is from Richard Smith, and he wrote this almost half an hour ago, and it was something that occurred to me. Circé, for your stacked anomalies example, how long does it take to place all the plates to model for formational conductors and any ore bodies?
That's a good question. To model the basin, I use the geological map as an influence, right? I know where there's a fold, and so I get the feeling of what's going on. Obviously, my work is not to make a perfect model of the basin, it's to track down the ore body. So I try to go straight to the point, but it can take, a day, 2 days at most. I think it's,
Really?
you've seen some of the fit. I mean, it's not perfect. It's just to get the feeling of what's going on, especially the dips, at orientation that can bring ideas to where the ore lines may be. So it's really decent time. It's not astronomic time to model the basin. And I usually start at channel 20, which is, I don't know, trying to remember, let's say 10, 15 millisecond after the current. So I don't model, gates 1 to 15. I will, focus on, mid and late time.
Yeah, I mean, it struck me looking at the way you approach this, that, a lot of what we do in the MT world is inversion. We throw our data into a code and we get a model out. And unfortunately, we often don't look at closely enough, I think, at misfits. And what you've done is shown just how very small features need to be explained. And those of us who do inversion might miss those small features, and those small features are giving you economic deposits, right? So
Exactly.
It's wonderful to see that there's a huge role for forward trial and error modeling still. Next one is Tyler Matheson. It's a very quick one. I may have missed it at the beginning when you laid out the geology. What's the age of the ore bodies?
It's 1.8 billion years.
Yeah.
I can have a look.
So around,
It's a good question.
yeah.
Challenging my.
Trans-Hudson age.
I'm scrolling back here. Yeah, 1.89 billion years.
Yeah, so the Trans-Hudson age.
I've put references in my geological slides, so people that are interested in knowing more about geology can actually read those very interesting papers.
Devin Cowan asks about a reference for the Maxwell modeling code. And I guess that's the code published by EMIT, right? Yeah,
yep.
Yeah. I'll put the link to that in the chat so that people have it if they're interested.
Thank you very much. There are a few modeling codes, obviously, that are available. Maxwell, I think, does a great job in our geological setting. There are plates, and the rest is free air, so fully resistant, and it's doing okay. It's fast, and level of precision that we need for our purpose.
Kyle Patterson says, fantastic presentation, as do a lot of others. There's a lot of people talking in the chat about what a great presentation you just gave, Circé. Thank you. What size of the loops do you typically use for BHEM surveys?
It will be, we're always concerned about minimizing the induction of the formational. So I like to keep the loop as small as possible. So I will narrow the size to, drilling depth. So basically, from 250 to 400 meter per the side square loops. Sometimes I like to do double turns. So we really, especially when there are lots of known lenses, sometimes we are, we have a lot of lenses that we know around and we need to really focus on that window. So I will double turn to just really focus the primary field on that. But I'd rather use smaller loops. And, so far we got, very good signal to noise ratios. And also near the mine, I noticed that if we are using two, large loops, because obviously we like to optimize the field operation. So we plan one loop that will be used for many drill holes, so we spare the legs of the guys. But if we're near mining infrastructure and we have two big loops, they become antennas and they grab all the signal from the activity. So there's a second reason why we want to, keep the loops as small as possible.
A question now from, there was a question I clicked over too quickly, from Deloro Fitlo. And this is one that struck me as well. Would borehole mise à la masse be used in such an environment to target disseminated sulfides?
I'd love to use mise à la masse. However, we are drilling in permafrost. And so the holes will just, freeze in 36, 48 hours. Okay. So it really prevents us to do to gather physical rock properties in situ. We do it at the core shack. We have enough time to do our 2 borehole EM surveys with both loops. Yeah. However, after that we need to get out of there. So
I guess you could, if you had a cheap electrodes, you could put those down and let them freeze in place and have that as a transmitting hole.
Taking note.
A question from Thibault Aztec. Thanks for the very interesting presentation. Slide 26. I don't remember.
Yeah.
You seem to have a very strong negative signal in the Z component of the EM response.
Correct.
That I don't think you fitted. Potentially indicative of a strong IP response. Can you comment on that? For example, have you experimented using IP in EM to detect and characterize disseminated sulfides? And IP was going to be one of my comments as well.
A very good question. 2 things in that slide. When conductors are running parallel to the survey line, they will often yield a negative response at the low part of the M shape. And also when conductors are really shallow, it's systematic. We see that the minimum between the 2 peaks are actually going in the negative. My impression was that that was associated to geometry. However, it's not impossible that it's associated also to IP if the negative remains in the late time. I have not shown any example of that, but we did acquire a moving loop ground data 2 years ago over an area, and it was the first time there was really distinct negative signature, and I'm sure that was IP effects. Unfortunately, it's hard to justify drilling just an interesting negative signature if there's no interest with exploration purpose. So we have not drilled it yet. It remains there, and maybe at some point in the coming years we'll have more information saying that it's interesting to go there. But at the moment we have no evidence that the ultramafic is running there, and so it's just waiting. But we did see what I think is IK effect on the late time of the B field profiles.
Devin Cowan. Compared to the Helitem data, the ground TEM data collects data at later times. Although they're imaging the same target, did you notice a difference in the recovered conductances from each data set? And I think you showed that, right? You showed that the Helitem was a much narrower conductor, and the ground TEM was a broader conductor.
Yeah.
More importantly, would you over or underestimate the conductance of the plate if you don't have late enough time channels?
I modeled the VTEM data that we have from our historical database sometimes when we don't have squid coverage over there, and it's working. It's just that the plates will end up to be 50 Siemens, 80 Siemens. We absolutely get no information on their true nature, conductive nature. Is just it's hard to determine whether they are flat lying or vertical also sometimes. So it gives a really rough mapping of the conductors. Sometimes, if we have nothing, it's better than nothing. But yeah, definitely the system doesn't stay in place long enough to really be able to characterize the conductance of those features.
If I can ask you don't have to answer this if it's proprietary information, but you showed how much stronger the anomaly is in the ground-based measurements compared to airborne measurements. What's the relative cost of a VTEM survey to a ground-based survey?
I think we all agree that, airborne surveys are faster and thus cheaper, right? Yeah. Because we cover so much ground in a blink of an eye, and performing moving loop ground acquisition is definitely a hard work. And I take a moment to thank all the guys that go out there every winter, to collect those precious data. I think it's complementary information, because where will you put your squid grids if you have no information, right? So
exactly right.
Very justified to do a first pass regional scanning, using an airborne, knowing that you'll probably just pick the shallow and easier targets, but
right.
It's part of the plan, to success. There are some steps that are right. Better to do at the beginning, and then if it's worth it, you make more work.
Right. And then one more question from Chushan Lu. I may have missed it, but how is the cultural noise affecting the data?
We have sometimes we're impacted by solar storms, for instance. So I include that in the cultural noise. So we have to look for the storm weather on a regular basis to make sure that if the data are just wrong, we know where it comes from. We have 2 communication towers that will cause problems if we need to survey too close to them. Fortunately, we know where they are, and we completed our survey near them. I mentioned about the loop size. We realized, because we're exploring again, brownfield near open pits and stuff, and that loop over the pit I showed earlier, it has to be like this, because there's no way we can hang the cable through the hole. Right. And that loop, the results are always more noisy, because it's 900 meter long, and it does act as an antenna and capture the signal from the cam. But other than that, like the rock trucks and the circulation and that has no impact on the data. Honestly, the data we collected so far is always of great quality.
It looked very nice. Yeah. And you can't use the signal from the, or sorry, you can't use the noise from the communications towers as signal, actually.
We could. That could be interesting. It would be interesting to see what's the frequencies and the repetition of the signal to see if there's something that could come out of there. We don't have any power lines. Everything is powered with generators.
Okay. And another question that perhaps you might not want to answer, but just to give people who are not that familiar with exploration, especially up north, how much does a drill hole cost?
We usually say $1,100 per hole. Usually, that's kind of a rough number. So
100,000.
Yeah, sorry, I'm not good with the numbers in English, but yeah, 1 and 5 zeros.
Yeah, not 6 zeros, but 5. Yeah.
Yes, not a million, but yeah, 100,000. Yeah.
Yeah, because you can do an awful lot of geophysics for 100,000. So it's
well, it's
yeah,
it's we always need to evaluate if it's worth drilling, right? Because it's a lot of money drilling holes, and that's the price. That's the standard price that everyone says. But drilling in such a remote environment with every material coming from south, and it's so expensive to bring in equipment and personnel. So it's probably much more than that.
Yeah. No, my feeling is that often the companies run to drilling a little too early, that they could get more out of the geophysical data because the holes cost so much. And then subsequently, after the drilling, they don't go back to the geophysics. You have knowledge, right? You now have knowledge, and you can use that knowledge to further constrain your modeling, go back to your data.
It's extremely exciting and rewarding to see the drilling results and to work among geologists and to discuss about the intrusive, the shape, the footwall, where the magmatic footwall is, and it really allows to extract all the juice from the geophysical signature. You really get totally enhanced interpretation.
Well, there's no more questions, and it's getting a bit late, so I'd like to thank you again, Circé, for an absolutely wonderful talk, a real insight into how far you can go with geophysics, providing you carefully each step of the way. So thanks again. And someone's asking the recording, it'll be available on the MTNet YouTube channel within a couple of hours. And Circé will send me her presentation in a couple of days, and that'll be on the MTNet EMinar page. Thanks, everybody. See you next week.
Thank you very much.